Thank you very much. It's a great pleasure to see you. My name is Willem, indeed. I'm happy to talk to you about decision diagrams for optimization. I am at the Tepper Schools for, I think, 18 years now, 19 years. And this project on decision diagrams started right when I started at the Tepper School. One of my colleagues over there, Professor John Hooker, some of you may be familiar with his name. He's been very influential over decades, actually. He had a very, very nice paper in 2007 using decision diagrams in the context of constraint programming. When I read that paper, it was really eye-opening to me. And even though it was in the context of constraint programming, I saw the applications throughout all fields of optimization at that time. Of course, not at the level that I have right now, but it was super exciting to me to start working with him and to students, David Berkman and Andre Sire. And over a number of years, we developed tools for optimization based on decision diagram technology. The book that we have here from Springer 2016 collects some of these materials, and I will go over some of those as well here. I think it's about 50% of the tutorial that's also covered in this book. But since 2016, there's many other developments, and I'm going to touch on those as well. I have a URL to my website here, so all the materials, the link to the tutorial, for example, is on that website, and some of the papers as well, some code if you want to check that out. Okay? So let's get started. And decision diagrams are not commonly known to the operations researchers, even though some people in configuration may have heard of them, but it's a very well-known technique from computer science. And in fact, it was one of the highest cited papers, one of them by Brian, that introduced the decision diagrams for verification as a very scalable way to do formal verification. And this was in the late 80s and the early 90s. So a decision diagram was originally introduced as a way to compactly represent Boolean functions. And a Boolean function has Boolean variables, here x1 through x4, and they can either be true or false. And a function is an algebraic representation of a function that is either true or false. So in this case, f is asking that the Boolean variables x1 and x2 take the same truth value, and also the variables x3 and x4 take the same truth value. So that formula there is an algebraic representation. So it's a compact implicit representation. And sometimes, of course, you want to find out what is the truth assignment to that formula, which itself can obviously be NP complete. Another way to represent that information is as a table with all the tuples listed out for the truth values of the variables. So you see that in the left bottom, and you can then evaluate, just plug in those values, is the function true or false. That's another way of representing it. It may not be that smart because it's going to be an exponentially long table, okay? But there are benefits from having this information directly at hand, and so that's very interesting to somehow have that explicit formulation available to you, and that's exactly what decision diagrams will give you. Decision diagrams are a compact representation of the explicit set of tuples that will either evaluate the true or false for this function. So a decision diagram is a layered graph, it's a directed graph, and all the variables that we have here, x1 through x4, is an imposed ordering, and you can take any ordering. That means the decisions you make in this decision diagram have to follow that prescribed order. You start with x1, then x2, and so forth. You have two types of arcs here, the dashed arcs and the solid arcs. Dashed are 0 or false, and the other ones are true. So if you, for example, follow me along the left path, and x1, the Boolean variable, takes the value false, and then you follow that with the decision for x2 being true, you see from the equation that x1 has to be the same value as x2. So as soon as you have a true, false, or false and true for x1 and x2, you know immediately you're not going to satisfy the formula, right? So then you can jump right to the terminal that says 0. 0 is the false terminal. On the other hand, we have the 1 terminal, it's a true terminal, and for example, the path 0, 0, 1, 1, or false, false, true, true, says that x1 and x2 take the same truth value, and also x3 and x4. So this is a valid assignment, and it leads you to the terminal true. Okay? In other words, this is an explicit representation of all possible truth assignments, and you can query this diagram and readily get an answer, is the function true or false. That's it. There's two types that we will consider, binary decision diagrams and multi-value decision diagrams. That has to do with the decision. It's either true or false, so 0, 1, it's binary. And multi-valued is an integer set, for example, of integers, or it is another set of elements that you can have as decision values. This has been widely applied in circuit verification, formal verification in general for software and computer science. It's a very often used tool. There's a whole algebra you can build on top of diagrams. You can take intersections, you can multiply them and so forth to take subsets of constraints and then intersect them and so forth. And also in configuration problems you see this a lot. And some of you that work in production, may have seen this before. In configuration you have oftentimes exponential, possibly exponential set of configurations. This is a compact way to represent these. However, we will not use this set of decision diagrams in this form. We are interested in optimization problems, but this is the inspiration. And so what's the optimization view here? It's rather than having Boolean variables, we have numeric variables for optimization. So the literals or the Booleans will become the variables, the decision variables, 0 or 1 rather than false and true. And the paths here will become variable assignments. And that will be your solutions indeed for your optimization problem. So here's an example of an optimization problem on the left top. It's an integer program with binary variables now. It's exactly the same application, by the way. I impose that x1 equals x2 and x3 equals x4. Okay? So if you look at that linear set of linear constraints there, that encodes exactly this Boolean function. x1 equals x2, x3 equals x4. So I turn the Booleans into binaries, so they're numeric now, and the constraints are linearized. It's another way to implicitly represent this constraint set, right? Let's drop the objective for now. But if you just look at the feasible set for this linear program, this integer linear program, it's of course exactly the same feasible set as for the Boolean function. It's encoded just as numeric variables now. So what we can do, you can drop the 0 terminal, the false terminal, because for optimization we're not interested in infeasible solutions. So I'm going to clean up the diagram and I just keep the paths that lead to the true terminal. Sounds good? I think so. So I clean up the one terminal as well because I have only one terminal left now. And all the paths from the root to the terminal, for example, well, you saw that 0, 0, 1, 1, for example, are now solutions to my integer program. So this is a compact representation of the solution set for my integer program. It's an explicit representation. It will be exponentially large in principle, in general, but it's still nonetheless an explicit representation. Okay? So all the solutions are right there as paths. And that's the key to using optimization, decision diagrams for optimization. The other very nice thing is I have a handle on all the decisions as arcs in this diagram, and I can bring back the objective function. For example, if I choose to select for x1 the value 0, the contribution to the objective will be 0. It's 2 times x1. If I choose 1 for my x1 variable, the contribution to the objective will be 2. Right? The coefficient is 2x1. And I can do the same for every arc in this diagram. For every arc, I have a decision. For example, x2, x3, x4 also have their 0, 1 decisions, and I can compute their marginal contribution to the objective function. Okay? Good. If you agree with me, then we can compute now, for maximizing this objective function, a solution by taking the longest path from the root to the terminal. Any path from R to T, from the root to the terminal, is a solution, and I take the one with the longest, with the maximum weight. So I convert an implicit representation as a linear set of constraints with an objective function. I convert it into an exponentially large layer-directed graph where every path is a solution. So there's a one-to-one mapping between solutions to the integer program and a path in the diagram. And there's also an associated cost with that. And I can now, instead of solving the integer program over this linear set of constraints, I'm going to solve it as a longest path in the diagram. But if I minimize, I take the shortest path. This is a directed acyclic graph, so optimizing a longest or shortest path is linear time. So that's very, very easy to do. So if you can convert an integer program into this form, optimization is straightforward. So problem solved, all integer programs are solved. Obviously it's not that easy because these things can grow exponentially large. And that's the problem, but we have a fix for that, and I'll show you that in the first topic. That's a branch and bound solver you can build on decision diagrams. That's also what the book is mostly about that I showed you in the beginning. We use dual and primal bounds based on decision diagrams and embed it in a branch and bound search. It's a standalone solver and has some competitive results in some domains. The other application areas are in constraint programming and integer programming. So they are, of course, well-established frameworks of computation by themselves, but you can use decision diagrams to improve those computations. So I'll show you how you can do this. And the last topic today and of the tutorial, I will present something called column elimination. It's very closely linked to column generation that's used for large-scale integer programming problems that have specific structures like vehicle routing problems, scheduling applications, and so forth. And there's a very nice connection with the pricing problem in column generation, which is often using dynamic programming to solve. And we can actually use decision diagrams in this context in a very interesting way. So that's the newest work. There's many more things on decision diagrams. I can't cover that all today, but the tutorial has a long list of references with much more details, obviously. Okay. So we'll start with the branch and bound solver. And I wanted to introduce that to you by means of an example application. And the application I'm taking here is a very classical combinatorial optimization problem. It's the maximum independent set problem. On the left we have a graph, and the vertices are labeled A through E, and every vertex has a weight, 5 for A, 4 for B, and so forth. An independent set is a set of vertices that are not connected by edges. So for example, A and D don't have an edge in between them, so that's an independent set. I want to find the subset of vertices that has the maximum weight, and that's in this case B and E, weight 12. Okay? It's an abstraction of many practical applications. It's one of the hardest combinatorial optimization problems out there. Also, computation needs not straightforward to solve these large-scale applications. But there's applications, for example, in scheduling, social network analysis, and so forth. So that's the application, and to get a feel of what we can do with this application, I thought it would be nice to run this first as an integer program. And so how do we solve this problem as an integer programming model and then give it to a solver like Cplex or Gurobi? So how would you build an integer programming model for this problem? Well, we have to select a subset of vertices, so it makes a lot of sense to have a binary variable, one for each vertex. So we either pick A or not, B or not, and so forth. So XA, XB will represent this. And if I pick a vertex, I will include the weight. So the objective will be 5 times the binary variable representing do I select that vertex or not, and so forth. Sounds good? And then we cannot have, for every edge, that both endpoints are included, because an independent set must have either one or none of the endpoints of every edge. So I have for every edge a constraint saying that either one of the endpoints or not more than one of the endpoints can be taken. So XA plus XB is at most 1, and so forth. And of course it has to be binary, so I have the binary constraints at the bottom. So you can see that this is a very nice formulation. If you give this to a solver like Gurobi or Cplex, it will be fine, although the linear programming relaxation is typically rather weak. There's a lot of interconnections here. For example, you see a clique of size 3, B, C, D on the right, but it's not in the constraint set. So you know that on that clique you can only pick 1. And that's missed by the linear programming relaxation by default, but you can add all those cuts and so forth. But that will be more work for the linear programming solver. So I'm just sketching what a linear programming solver and integer programming solver will do there. And there are some complexities here. But here you get a feel of how you solve this in linear programming now, or in integer programming. How do we do this with decision diagrams? So we'll take a different approach here. So I first want to sketch to you how do we build a decision diagram for this problem. We will still have to make the decision, do we include a vertex, yes or no? So my decisions will be XA, XB, XC. It will be the same decisions as in integer programming for this case. I like those decisions. I will just order them arbitrarily A through E, okay? And so the decision is, do I include a vertex or not? 1 or 0. So again, the dashed arcs are 0 and the solid arcs are 1. And what I need in decision diagrams is a way to compile these things. And you need some information to carry from one state to the next. And in fact, the underlying model that we use, and I won't show that here to you explicitly, is a dynamic programming model. And so these nodes will correspond to states in the dynamic program. So the root state is your initial state in your dynamic program. And from there you can take a transition. You can either transition via the 0 or via the 1 label. And that brings you to another state. For example, if I choose to include vertex A, I can no longer include it in my remaining graph because I already selected it, but also none of its neighbors can be included. I need to find an independent set. So if I pick A, I cannot pick B or E. You agree with me? So if I take the one arc and I go from the root to the node on the left, the remaining vertices I can still take are C and D. So in the terms of dynamic programming, my state will be the set of eligible vertices I can still add to my independent set as I go along the path in the diagram. And when I make a transition via either 0 or 1, I will have to update the state accordingly. For example, if I take the 0 decision from the root state, I have not yet selected anything. I can no longer do A because I choose not to do that. And the remaining set is then B, C, D, and E. Okay? I choose to compile it in this way, and we'll see where that brings us. So in the next stage, I have two states for selecting B. On the left side, you see that the graph induced by that state has vertices C and D. This is the set of eligible vertices. So if I have selected A, remaining is C and D as possible options. The choice is for B. Can I select B? No, the eligible vertices are either C or D. So on the leftmost node, I can only select the 0 arc. That's the idea of this state representing the set of eligible vertices. On the right, however, I have B, C, and D, so I do have B, and I can still split it in 0 or 1. I can make that decision. So I update the states accordingly, and then I have three states, CD, E, and CDE. Again, they all encode subgraphs. I continue. For C, I now have a choice in the leftmost node. In the middle node, I don't have a choice. On the right, I do have a choice for C. So that's the remaining. And now something interesting happens here. I have 5 nodes, 5 states, if you wish, for this fourth layer. And you can see that 2 of them are the same, the states E. So I can merge them because they represent the same set of paths. And one way to look at this, why we can merge them, is the set of completions are the same. All these states represent subgraphs, and they represent in themselves a set of independent sets I can still add to my current set that I have constructed so far. And so, in fact, the information encoded in the state is sufficient to prove that 2 states are equivalent. I can merge them and don't lose any information. And here is the full complete diagram. So if this is the first time you see this, I think that rule is maybe a little bit arbitrary, and it's not straightforward in general to find a compilation method and an equivalence rule to make sure that 2 states are indeed the same. In this case, the state information itself is sufficient to compile an exact and uniquely reduced diagram. This is reduced in the sense there is no smaller diagram that uses the same variable ordering. And for every combinatorial problem or Boolean function, there exists one unique reduced diagram. Using this state representation and this dynamic program transition, this model gives you, in a top-down compilation, the unique reduced diagram. This is not always easy to do. Sometimes the equivalence test will be NP complete by itself. It's fine, you don't necessarily need a reduced one, but if you want a reduced one, smallest possible one, then it may actually be challenging to get it. In this case, we are good. Okay? Now, every one of these transitions also has weights. Yes, you have a question? The question is, why do I take the D equals 1 arc on the right? You mean from level D, XD, you take the rightmost node DE? Yeah, so if you select D, then you will wipe out D and also its neighbor E, so you have to go to the empty set and you merge it with that. Okay, sounds good. As we compiled this based on another question, yes?
So you mentioned that this is the reduced diagram for this particular ordering.
Mm-hmm.
Is there any result on more generally for any ordering, like the minimum size?
Yes, yeah. So the impact and the effectiveness of these diagrams are heavily relying on the variable ordering. Finding the optimal variable ordering which results in the minimum overall diagram is an NP-hard problem. That does not mean that there are not good heuristics, for example. And you can even study if certain orderings, if that gives you a bound on the size. We have one paper in which we give some general results for this independent set problem, for example. One very interesting result related to the Fibonacci number. So the size of the ith layer is related to the Fibonacci number of that layer, of the ith Fibonacci number.
It all relates, right? Dynamic programming, recursion.
Yes, it does, yeah. There's very nice connections with theory here as well. Yeah. So I'm not talking about it here. Yes, another question.
So you said that maybe I missed a mistake. Sometimes the equivalent states are one when the remaining set of variables are equivalent. But it's not just that, it's also which variables have already been given values, right?
Okay. So the question is about the equivalence test. So I said to you we can merge in the 1, 2, 3, 4th layer those A states, because they represent the same subgraph and the completions are therefore the same. They're equivalent. For this approach, actually, all the states are Markovian. You don't care how you got there. You can have multiple paths into a state. It's irrelevant. And the Markovian property will indeed ensure that this equivalence test is sufficient. The equivalence test is not always immediate from the state representation. So if two states are exactly the same, clearly they are the same. But they can still be different, yet encode the same set of, exactly the same set of completions, and that's not easy to determine.
In this particular case, you have like 3 nodes in the graph, you have exactly
I see, yeah. So the question is about the nodes being states, and there are 3 ones labeled. In this case, what I choose to do is I keep every layer exactly you cannot have long arcs in this representation. You could, in fact, it's a zero suppressed decision diagram, jump immediately from the second layer to the last layer with E there. You can do that. You can skip over layers. For the sake of simplicity, I'm not doing that here. So under the assumption that we have no long arcs, this is the unique reduced diagram. If I remove that assumption, I still have the unique reduced diagram with long arcs. Exactly. So thank you for clarifying. There's a lot more technical details in constructing these things. I'm skipping over them, but the tutorial gives you references. So let me now move on and look at the optimal solution here, because you may remember there's an optimization problem underlying all this. We have the weights associated with the vertices, 5, 4, 2, and so forth. And every decision gives you either that weight or 0, right? So for example, if you take A, you get 5, you get that reward. If you don't take A at the top, you get 0 as a reward. So by our previous reasoning, we can now take the longest path. We are maximizing the weight of the independent set here, and find this path 0, 1, 0, 0, 1, which indeed selects B and E as the independent set. That's exactly the optimal solution. Okay? But the problem is, as I already alluded to, this is exponentially large to build these diagrams in the worst case. So how do we handle this? And the way to handle this is to forcefully merge nodes that are not equivalent. I impose a maximum limit. The width of the diagram is the size of the maximum layer. So in this case, on the right here, we have a width 3 diagram. Suppose I want to impose a maximum width of 2. Then you have to merge states. That's what we'll do. And we'll introduce a merging operator. I'm not going to formally do it. There's papers that do that. I'll give you the example, and then you get the gist. There's 2 requirements. If you want to merge nodes that are not equivalent, you have to make sure that you're not throwing away any solutions. If you create that new state, there must be a definition for the new state. And also the path costs may be relaxed, and you have to make sure that the path costs also remain valid for the original problem. Those are the 2 requirements. So let me have a look at this application again. Suppose I impose to you, you can compile your diagram, but I give you a maximum width of 3. So in any layer, you cannot have more than 3 nodes. Let's go. I'll compile it, and it's all fine until this layer right here. I have 5 nodes. Okay, we have the 2 E nodes. They are equivalent, so I can already combine them. But I force you now, in the remaining 4 nodes, to merge 2 other nodes, because you can have just 3. Which one would you pick? Well, I would pick one that is most related to another. So I want to lose as little information as I can. And also, what is the result of this state? How should I label this state? So if I have 2 states E, of course, the result will be state E. But I'm going to partition it into the E state and the DE state. I'm going to choose to merge forcefully the D and the DE state. What is the result of that state? And I cannot lose any solutions. And remembering that these states represent subgraphs on DE and on D, what I will do, I'll take the union of the states in this case. If I take the union of the states to represent the new state, I'm sure that I will lose no solution because all vertices that could still be included in either one of the states can still be included now here. So formally we have a merging rule that gives, so a function if you wish, it has as input two states, and the output is a new state with a merging the states, in this case the sets, but there can be other components that you have to merge together. So you can use intersection, you can use union, you take the minimum for integers or the maximum of integers to get a valid state representation as a result, in general. Doing so, we have now a width 3 decision diagram. Okay? But we know we have messed up in a sense. We have over-approximated the solution space. We have probably introduced new solutions that are not actually solutions. So let's look at the exact one on the left and the relaxed one on the right. Because we have merged in the proper way, we are over-approximating the solution space. On the left, we have the exact solution space. All solutions are there as paths. All solutions are also in the relaxation because it's an over-approximation. We didn't throw out any solution. But we may have introduced non-solutions, and here's a solution that we introduced, 1, 0, 0, 1. That corresponds to taking A and E, and if you look on the right at the graph, A and E have an edge. So that's not a solution. But that's fine, it's a relaxation. Okay? Just like linear programming doesn't give you an integer solution, doesn't mean it is useless as a linear relaxation. You over-approximate the problem to get something easier to solve. I have a limited width decision diagram. It's of polynomial size, the width times the depth, n times w if you wish. And if I now add the weights back into this, what's the result here? Well, on the exact one, obviously, I have my optimal solution with value 12. That solution lives also in my relaxation because it's an over-approximation. So that's fine, I don't lose that. But if I optimize over the right one, I'll get actually as optimal longest path this one, 1, 0, 0, 0, 1. It's an infeasible solution, which is fine for bounding purposes. This gives me an upper bound, a dual bound. Okay? So what I just did, I gave you a discrete relaxation that I can control. If you have a larger width, you get more refinements, and you can get a stronger bound. Okay? And in this day, we have no memory issues in terms of a computer memory. And so if you want to have a stronger decision diagram, you just build yourself a larger one, compile it, and get a stronger bound. Okay? So this is key to getting the dual bounds. But we still don't have a solution. We just have a bound. So the other ingredient for our framework is an upper bound, or I should say a primal bound, pardon. And what I mean by that is we are going to use restricted diagrams that encode a subset of the solutions. And here's the example again. Here's the exact diagram. This is of width 4. And again, we impose a maximum width of, say, 3. Here are all the exact solutions, all the exact paths. How do I get a subset of this? Guaranteeing that all the paths that remain are feasible solutions. It's not so difficult. You just drop states you don't like. Why don't we drop the rightmost state and its arcs? Boom. The remaining paths are still solutions. I didn't touch them. And I have now a width 3 diagram, which is encoding feasible solutions, but not all of them. Done. This can be done extremely fast. Maximizing over this, the longest path gives you a lower bound of 12. 4 and 8, taking B and E. Okay, which happens to be the optimum. Okay. So we now have 2 ingredients. We have dual bounds from relaxed diagrams. We have primal bounds from restricted diagrams. Similar to linear programming relaxations in integer programming and, say, heuristics like RINs or local branching and so forth. We still have to branch. And normally in integer programming or constraint programming, you take a variable and you split it in either it's 0 or it's 1. You take another variable and you do branching on variables. We could do the same here. But we can do something way smarter, and the idea is that our diagram actually encodes the branch and bound tree as well. All the possible solutions are there. The branch and bound tree is also in here, although you would normally terminate and prune states when you prove of suboptimality. But we have already done a lot of branching, especially at the top. We don't want to replicate that work. So how can we branch smarter here? We will branch on states in the diagram in the following way. This is our relaxation. It gave us a dual bound of 13. And there was this one state right there that's marked red. That was the merged state that was giving us the relaxation. You will recall that state, right? That's in the 1, 2, 3, 4th layer. The third layer is the last layer in which all the states have not been forcefully merged and are still exact in that sense. They are exact representations so far. Nothing has been messed up with. If there exists a solution from the root to the terminal, it has to go through one of these states. A solution is a path, so it has to cross the last exact layer. Okay, great. Ingredient 2, all of these states are Markovian. They don't care about paths coming in, going out. They are just independent subproblems. Great. They also have associated graphs, namely their states, CD, E, CDE, and the lower bound, or actually the exact bound found so far. So I put them all in a queue. Every one of them can be solved separately and individually, and independently. And we can recurse on the states. I can pick any one of these states from the queue. I built another relaxed and restricted diagram, and I recurse and recurse because I will have a last exact layer, put them back in the queue. In this case, what I will have, I have 3 subproblems. Luckily, they all have width 2 or 1, and I can now easily compile them, and I read off that the exact solution is 12. Normally, you would have another last exact layer, and those states can be put back into the queue, and they may actually take over, if you have a priority queue here, which we have, from other states you have put in there before. Okay? So that's the branch and bound framework. It's very different than what you would normally do. But in fact, what we are doing here, and I didn't show you the formal dynamic programming model, this is a solver for dynamic programming models that uses branch and bound. Normally in dynamic programming, we do state expansion, and hopefully it will be fine. Here we don't need state expansion per se. We have a limited width state expansion to get us primal and dual bounds, and the branch and bound will take care of the solving, just like you would use in the integer programming solver. So it is a solver for dynamic programming models. So how does this work in practice? Well, these are results from the book, if you wish. Here's comparing Cplex in green at the top and the BDD solver at the bottom in blue. We have randomly generated instances for the maximum independent set problem with varying density. So the number of edges in the graph gives you the density of the graph from 10% to 90%. And these problems are very sensitive to the density in terms of their computational difficulty. And you can see on the horizontal axis the density, on the vertical axis the average percent optimality gap. And these are instances with 500 variables, and you can see that Cplex can actually not solve any one of these on average. And the BDD can solve all of them optimally from density 50 onwards and is outperforming Cplex on these problems. Here is with 1500 variables, and the picture is even starker. So this is one example that shows that the technology can actually work and can be competitive with or outperform integer programming on an application domain like this. Now, this is not a magic bullet. I'm not going to guarantee that it will always win, and it doesn't have to be, but it's a nice addition to your optimizer's toolkit. Okay. We also applied it to other applications. One of them was the maximum cut problem, which is very interesting because there are not really constraints. It's another combinatorial optimization problem. And at the time, 2015, we compared this with the best known solutions from the literature. That can be anything, so this is just the best known results. And Big Mac was the solver based on SDPs and other very strong relaxations. That was the state of the art and still is a very, very good solver. And we found some instances on which we improve on the state of the art in terms of finding better lower upper bounds for the maximum cut problem, which was quite surprising to me that it could even do that. So as a branch and bound solver, it actually performed quite well on these classical combinatorial optimization problems. Okay? So that concludes the first part of the talk. the branch and bound solver, and then we looked also at other application areas, and the origin actually of decision diagrams for these kind of problems came from constraint programming. I know that some of you have heard of this, but maybe don't all know the details of constraint programming. We don't need a lot of information to understand what we need for the decision diagrams, but I want to give you an overview of the key technology in constraint programming, which is called constraint propagation. So in constraint programming, you don't necessarily have a linear relaxation. You have a set of constraints. It can be anything, like all different, or you can have strict inequalities. But you do have, in this case, discrete domains. So you can also have continuous domains for this application. We just have discrete domains. So the idea of constraint programming solvers is, rather than having this large linear relaxation, we take the constraints individually, and every constraint has its own individual algorithm to remove infeasible values from the domains of the variables. So for example, if we look at the first constraint, x1 should be strictly greater than x2, I can remove some of these domain variables, 1 for x1 and 3 and 4 for x2. Okay? Then we go to the next constraint using these updated domains, and we can see that the only remaining variables, or we can now exclude more variables from these variable domains. So we need a proof of infeasibility to remove these values per constraint. Okay? And then for the all different, which says that they should all take distinct values, I have another chance to refine these domains, and here's where we are. So if you are lucky, this process will continue until you reach a fixed point that is actually a solution. Here we have 2. 1, 3, and 4 as a result. So we were lucky. Normally you have search on top of that. So that's the idea of propagating domains through the constraints. And it's not obvious to everyone that actually what we're doing here, we're propagating domains. And every time you're leaving a constraint, all the work you did in that constraint is lost. For example, for the all different, the algorithm that uses the all different propagation is based on matching theory. So the algorithm builds a matching, it identifies values based on that to remove, and then it leaves the constraint, and that's that. But there's a lot of structure that might be useful for other constraints, but you just don't know it because you have to propagate the domains. Everything, all the information is projected back on the domains. And that's sometimes problematic. For example, here's another example that's very similar, but domain propagation doesn't do anything. You have to do these things separately. So let's just take a minute to understand why this does not work. We have 4 variables, x1 through x4, and they all have to take values 1, 2, 3, or 4. They have to be distinct, fine. I can find any permutation, but also the first 3 variables should add up to at least 9. Okay. So if I pick any of the variables to be 1, I don't have enough room anymore to satisfy the second constraint. So you know that x1, 2, and 3 cannot be 1. They must collectively be 2, 3, and 4. So then we can also know from the all different constraint that the reasoning here is that we have integrated all different and the linear inequality, if you take them together simultaneously. But the propagation can only handle 1 constraint at a time. And if you just look at that equality, I can take x1 is 1. Sure, I can. I can just take x2 and x3 to be 4 and 4. So for the linear constraint, I can take a solution 1, 4, 4, which does not satisfy the all different constraint, but that will be taken care of by the all different algorithm. So here's a chance where or an opportunity for something else. There's some information that is missing. So why don't we propagate decision diagrams rather than domains? We give every constraint a chance to propagate the diagram, refine it, and then give it to the next one. And it gives us an opportunity to get structure, more structured information from one constraint to the next, rather than just projecting back everything on the variable domains. So in the beginning of this process, here is a very simple diagram. It's the Cartesian product of all variable domains. All possible tuples from 1 to 4 are going to be here. 256 solutions are implicitly represented by the domain store of constraint programming. And we can't do any domain propagation because we just figured that out. But if we were applying the all different propagator to this decision diagram, it could do this. It could refine this and find paths that are not feasible and remove them and build this diagram for us. Now we only have 24 solutions left. This diagram is then given to the linear constraint, which then takes a shot at further refining it, leading to this final decision diagram. And it only has 6 solutions left. And you can actually see here the last layer, x4, has only 1 possible value, that's the value 1. We determine that together. 2, 3, and 4 are collectively taken by the other 3 variables, and now we can read this off. We can actually project it back onto the variable domains and get that information if you want to, and you can integrate it with the standard domain propagation of the constraint programming solver. So that's very nice if you can make this work. Now, again, we have to make this scalable, so you have to make sure that the decision diagrams are of limited width and so forth. And I'm going to give you an example on scheduling later there, but there's a question. I see, a very good question. So interestingly, the question is, does the order matter in which you give the decision diagram from one constraint to the next and so forth? In general, constraint propagation, so for this case, for example, the order does not matter, and actually every arbitrary propagation cycle leads to a unique and is the same fixed point, which is very cool under some assumptions. So it doesn't always work, but if the propagators have certain properties, then the ordering doesn't matter, which I think is very interesting. However, the properties are not satisfied by the decision diagrams because you have to make some choices on how you propagate them. For example, what is the maximum width? These are not in that sense complete propagators. I have to choose what is my width, how do I split, how often am I going to propagate these diagrams, and then the ordering does certainly matter. And for efficiency reasons, you typically leave the more heavy ones to the end. So you do the lightweight propagators first, and then the heavyweight propagators. Yeah. So let's see how this works on an example application. Oh, before I do that, let me just go back because I missed to tell you the following. Propagation means, in this case, the constraint gets a decision diagram and it has a chance to remove not just variable domains, but arcs from the diagram. An arc is now a decision, right? An arc has a value. So we can remove arcs that are not consistent with that constraint. And in fact, we can also use it for dual bounds by optimizing over the diagram later. And this was the paper I was talking about in the very beginning when I was so excited about this application, the 2007 paper by Anderson, Hatzig, Hooker, and Tiedemann, who first introduced relaxed diagrams in the context of propagation. And they already showed orders of magnitude possible improvement in terms of speed-ups for the solver. So there's a lot of power in these diagrams. Let's have a look at disjunctive scheduling as an application. It's a very classical application. Most of you will have seen this in one way or another. We have the framework of activities with a resource, a single resource. It's non-preemptive, so I cannot interrupt the task. If I start a task, I have to complete it. And you can only do one at a time. It's disjunctive scheduling. In this case, we have 3 activities. Every activity has a release and a deadline and a certain processing time that it has to take up on the machine. Objectives can be minimized make span, sum of completion times, tardiness, and so forth. We can handle all of them. And there can be side constraints like you have to first do activity 1 before activity 2 and so forth, precedence constraints, for example. Question is, how do we build a decision diagram for a problem like this? Standard constraint programming solvers would use a start time variable for every activity and an end time variable and use interval reasoning, constraint propagation to tighten these intervals as much as possible until you have a fixed interval for every activity. But we don't do that in that way. What we'll do rather is represent solutions as permutations. If you have a disjunctive scheduling problem and you have 3 tasks, they cannot be overlapping. So one task has to be the first one, and then the second, and then the third, and so forth. So you have a natural ordering here. What is the first task to be executed? What's the second task? And what is the third task? So a solution is a sequence of activities. And that sequence is a permutation, pi 1, pi 2, up to pi n in general. Okay? So the labels for the arcs here, for the first decision, what is the first task that we can do? I have an instance with a precedence constraint that I say that the task activity 3 should come before activity 1. That means that my first activity cannot be 1 because I haven't yet done 3. Okay, so I have 3 tasks here, or 3 activities, 1, 2, and 3, and the precedence constraint says I first have to do 3 and then I have to do 1. So the only choices for the first task is either 2 or 3. And then I can see that I can do either for the leftmost branch, you can then do 2 or 1 and so forth. Here are all possible solutions for this particular application. And here is a solution, ordering 3, 2, 1 as the activities. And now I can infer the start times from this permutation. So rather than using the start times as my decision variable, it's inferred automatically from the permutation. Okay, now for some objective functions, you still have to decide on the end times and the start times, for example, tardiness or lateness and so forth, so it will become a decision variable then, but the core scheduling is only driven by the permutation. Does that sound good to you? So a solution can be represented as a diagram or with all permutations right there, and I filter out those, I remove those that are not feasible solutions. All right, how do we build them? How do we propagate these things? Well, we have several constraints. We have the all different constraint that gives us the distinct values, so the permutation structure. We have earliest start times, latest end times, and then we have precedence relations or anything else you want to add on top of this. And they will be separately given a chance to modify and refine the diagram. Each one of them will have its own chance to do this by state information that we keep at each of these nodes. So for the all different, we want to understand which tasks have we already executed, so that we don't repeat those tasks. For the earliest start time and latest end time, we have to keep track of those informations as well at the states. Okay? So how does that work? When we propagate this disjunctive scheduling application, again, we have the precedence constraint here. I start with a very simple the with one relaxation, the Cartesian product of the variable domains. There's a lot of repetition here, obviously, but that's fine. And we will compile this from the top to the bottom, layer by layer, and get the constraints have a chance to do their propagation. And that means removing infeasible arcs, or refining the diagram if there's still room. So because of the precedence constraint, 3 must come before 1, I cannot do activity 1 in the first layer. So I'm going to look at my top layer, and I remove activity 1 as option. That's my propagation, removing arcs, based on the constraint that represents that precedence. That was that. What I have now is an updated diagram for the first layer. And I recognize that 2 and 3 in the first decisions are not the same, so I can split them. And I copy the outgoing arcs for both of them, and I split the diagram and refine the diagram as such. This diagram encodes exactly the same paths as the one on the left, but it has one split. But all the paths are still there. Do you see that? You do. But because of this split, I can now propagate further in the second layer. So we're going to consider the second layer and do updates. I have an all different constraint, and I can remove 2 from the second layer on the left and 3 from the second layer on the right. So the all different constraint can remove arcs. I still have my precedence constraints. I invoke the precedence constraint again, and I can remove the 1 on the left. There we go. Now I've done my propagation. Chance for refining. Can I split something that is meaningful? I choose to split in the following way. There's 3 paths coming in. 2, 3, 3, 1, and 3, 2. I'm going to split in the following way. I split off 1, and I keep 3 and 2 together. That means on the leftmost node in the third layer here, 2 and 3 are taken on any path from the root to that node. That means the all different constraint can determine that 2 and 3 can no longer be taken. On the right, the all different can determine that 1 cannot be taken and 3 cannot be taken. And there we have our final diagram. So the illustration here is that the constraints are given a chance to remove arcs, refine the diagram by splitting it, layer by layer. And then we end up, in this case, with the exact diagram. In general, you would have a relaxation, which is not necessarily exact, but still can give you very interesting information. For example, you can get bound information, and of course these other ones are still relaxed. So if we give back the instance here and we encode the bounds here, if we evaluate the optimization bound, the make span for example, we get a lower bound of 7 for the first 2 relaxations, and then we get the exact bound, exact solution for the final exact diagram. So we can still use these diagrams also for dual bounds. Sounds good? How does this work in practice? Well, this was implemented in the constraint programming solver CP Optimizer by iLog, CPlex solver. the state-of-the-art CP solver at the time, and still is very competitive in terms of scheduling. It's still an extremely powerful scheduling engine. And so we compared on the left on instances traveling salesman problem with time windows, which can be cast as scheduling applications, and you may know this. And we have on this scatter plot, which is a log-log scale in terms of time. So we have orders of magnitude differences there, right? So from 0.1 to 1 to 10 seconds and so forth. On the bottom, on the horizontal axis, we have the CP optimizer time to solve these instances to optimality. And on the vertical axis, we have the MDD time, adding the MDD propagator. And we turn off any scheduling algorithm that is in the CP optimizer. So it's either running the advanced CP optimizer or none of that and only the MDD propagator that we built. So if you look at one of these scatterplot points, that gives you the same instance solved by both the CP optimizer and by the MDD propagator. And in many of these cases, these instances are unsolvable by the CP optimizer, but they are solvable by MDD, and it can be 4 or 5 orders of magnitude difference in terms of solution improvement. And that is showing the power of MDD propagation in addition to domain propagation for constraint programming. And in fact, if you look at the traveling salesman problem with precedence constraints, it's known as the sequential ordering problem. There are open instances from the TSP lib, and we closed at the time 3 open instances for the first time using this technology. So another example of the potential of this technology. Okay. So that was the constraint programming part. I want to next switch to integer programming. So how can we use decision diagrams for integer programming applications? And I want to start with, again, representing integer feasible sets. In the very beginning, I did this for Boolean functions and then for general integer sets. So let's do the same thing now from an integer programming point of view. So an integer program, feasible set, is typically represented implicitly by a set of linear constraints. So I have a set of linear constraints right there on 3 variables, x1, 2, and 3, all binary. And you can see the polytope, the polyhedral representation at the top, encoding or representing those linear constraints. And the integer points are the feasible set. Okay, that's where we're used to this kind of representations. But the integer set can also be represented as a decision diagram. We knew this, so let's do it. I can take these constraints and I can compile a diagram representing exactly the integer set. Here's the diagram following the ordering x1, x2, x3. The arcs have labels with y variables. You can ignore them for now, but you can read off in the diagram from the root to the terminal once again, every path corresponds to a 0, 1 solution. That's an exact solution. So there's 3 points right there, or 1, 2, 3, 4 points on the left that are integer, and they're all encoded like 0, 0, 0, 0, 0, 1, and so forth. Okay. What's the connection here? Now the y variables come into play. The key to integrating decision diagrams in integer programming is to build a network flow formulation over the diagram. And you know that the shortest path is also a network flow of flow value 1, and that's how we will encode this. So a solution is a path in the graph. A path is a network flow of value 1. The decision diagram is a network structure, so the linear programming network flow formulation will give you an integer solution. So we have a nice encoding of all integer points as a linear network flow formulation. So what we have to say for encoding a path is, I need a path of value 1, leaving the root and entering the terminal. So the first constraint on the right top says the 2 arcs, y1 and y2, those variables should add up to 1. Exactly 1 path must leave the root. Then we have flow conservation. So for example, on the left, we have y1 flow, inflowing for the leftmost node for x2, and equals y3 plus y4. And we have flow conservation for all the intermediate nodes. And at the end, I make sure that we enter the terminal with exactly one unit of flow again. It's a redundant constraint, but I added here for completion. Now, the nice thing is we can map back this representation to the original X space. By looking, for example, at the decisions for x1. x1 is either 0 or 1, represented by the values y1 and y2. So if we want to map this back, I just say that x1 equals 0 times y1 plus 1 y2. And the 0 and the 1 are the values that they represent. So y1 represents taking value 0, and y2 represents taking value 1 for the variable x1. And same for variables x2 and x3. So on the bottom right, you see the mapping back to the x variables. Okay? And the nice thing is, the result that was already shown by Marcus Bele in 2007 is that this gives you exactly the convex hull of the original space. Okay? So the integer set in the original space can be, the convex hull of that can be obtained doing this. And that's a very nice, powerful mapping. And it's powerful because it gives you the convex hull. It is challenging to deal with because the decision diagram can grow exponentially large. But you do not need to do this for all constraints. You can also choose to do this for a subset of the constraints. And what is really nice, here I have a linear set of constraints. But the decision diagram doesn't care about linearity. It just cares about an integer set. If those constraints were quadratic or any other nonlinear form, or even a black box type of constraint that just gives you a feasible point, I can still build the decision diagram. And I can still do the conversion, and I can still map it back and get the convex hull. So this is a very nice way to lift the original problem into this, network flow space, an explicit formulation of these paths, and project it back on the original space. And this is not the first time this has been done. There's arc flow formulation in general for integer programming, so this follows very nicely that literature as well. The benefit is that the decision diagrams allow you to use the decision diagram literature to get these arc flow formulations for specific applications very efficiently and use relaxations. So applications are, for example, if you have nonlinear components in your model, like objectives or constraints, you can encode them as decision diagrams and just don't even map it back. Well, you map it back, but you don't have to do the projection back. You just give it back this formulation on the right. You have your network flow representation, the mapping, and you just dump that all in your integer program. That is the first application that's been very, very effective for quadratic objectives and constraints. And these are just some example papers. But any nonlinear constraint can be handled like this. Another application is to generate cutting planes. Some of these, especially nonlinear problems, can be very challenging to get good cutting planes for. Outer approximation relies on similar technology as well. And so if you represent your subset of the constraints or even individual constraints as a decision diagram, you can use this to generate cuts using, for example, a cut generating linear program. And then that is informed by the network flow representation. What you can also do is obtain dual bounds and integrate the decision diagrams inside the integer programming branch and bound tree. That's a little bit more complex, but it still can be done. And I wanted to give you an illustration of that, to give you some numbers here. So that means you have a branch and bound tree for the MIP solver, and you have a shadow model, the decision diagram, that is invoked at each node in the tree. And you run it, you get a dual bound, and a dual bound may or may not be better than your linear programming bound. If so, you can help to prune. And so the way that you could do this, you can identify a substructure, either a set of constraints or something that's built in the solver. We used the conflict graph, which is a nice binary structure, similar to an independent set structure, by the way. And what we also did, all the constraints that are not encoded in the diagram, we don't ignore them. We either do constraint propagation over the diagram, or we use Lagrangian bounding as well. So the details are in the paper, but you can get interesting dual bounds here. And if you do that, you can automate everything. It's, in this case, completely inferred automatically by the integer programming model. If you apply this to some random instances that we did, you can see that it gives you good speed-ups for this application. This is a best case scenario, so I don't get fooled here in that sense. This gives you a potential, but we found also for MIPLib instances, there was not as much power available to us to really exploit diagrams. It didn't hurt too much, but we also didn't get this great benefit. So this is really a best case potential scenario, but it's really application dependent whether or not this will work in general. Okay. Okay, I have a few more minutes for the last topic, a new topic, column elimination, which relies on several elements that we have seen, in particular the connection with integer programming. And the starting point of column elimination, which you'll be reminded of column generation, obviously, is the following. So let's take a step back and think about column generation for integer programming, and then starting with that, of course, for linear programming. So a column generation model has a column-driven linear program in which every column represents something like a route or a schedule, more complex thing. So a variable is not just one by itself a numeric variable. The variable represents a complex object, like a schedule. So if you take that variable, you take the entire route, you take the entire schedule. There's many applications that use this and have been extremely effective. These formulations typically have exponentially many variables, and in column generation, for a linear program, you only need a small subset to prove a small basis to prove optimality. For some application, and what you do then, you start with a small subset, you get dual bound or dual values, and you ask a pricing problem: does there exist a new variable, a new route, a new schedule that improves my linear programming model? If so, add that new variable and you iterate until you converge to the optimal LP solution. That's all fine if you can price efficiently. If you can query the subproblem, give me a new variable. In many cases, for example, for routing applications, asking for an optimal route is as hard as optimizing over the original problem to begin with. So you have an issue. Now, how to resolve this issue? You will relax the pricing problem. You'll ask something that is not maybe exactly a route, but it's almost a route, it's a relaxed route. That gives you a chance to very efficiently query good columns and then reach the optimality sooner, and don't have to waste your time on solving an NP-hard problem in the pricing problem. That's the inspiration. What we are trying to do here, and so I'll just skip through this, so some of the columns may be infeasible. So that's a starting point. What we're going to do is we don't want to do the iterative process. We recognize that the pricing problem is already there, and we can expose it as a decision diagram. And rather than doing iteratively adding columns, we solve the master over the pricing problem. And all the constraints that are normally in the master are now expressed over the decision diagram. And the decision diagram represents all the routes, represents all the schedules. Anything you want to represent in your pricing problem is now represented in the diagram. And there is no more master. There's just one problem, and that's it. And then that problem may be relaxed. You will have infeasible routes, but we will eliminate them iteration by iteration to reach something that is optimal. And I'll give you an illustration on the graph coloring application, and then I think that will become even clearer. Graph coloring is another classic in combinatorial optimization. We have a graph, say on the right top, and we need to give a color to every vertex so that two adjacent vertices have a different color. So here's a solution. There's many different integer programming and linear programming models for this. Some are better than others. One of the best ones uses column generation, a column formulation, in the following sense. A variable is not going to be what color to assign to a vertex, an individual vertex. A variable will mean what set of vertices that are a color class will I use. For example, the color class 1, 4 can be selected, or 2, 3 can be selected, or 1 or 2. We can enumerate all color classes, and a color class is actually an independent set. An independent set is a set of vertices that have no edges in between them. And if they have no edges in between them, they can all get the same color. And we can enumerate all of them. The set I there are all the independent sets, all the color classes, and I just have to pick a subset of these that covers all my vertices, and a minimum subset in the sense I need a minimum number of them to find the best solution. So xi on the left represents the variable selecting subset I, independent set I. And then I have covering constraints, making sure that every vertex is covered exactly once. That's the standard and very effective formulation based on column generation. And that's also the basis of what we'll do here. The independent sets can be exponentially large, but you know, we just did it in the beginning of the tutorial, you know how to represent independent sets. That was the first application we looked at to begin with, right? So you know, if I give you a graph, how to build the diagram. We know how to do it. Here's the diagram for the independent set problem. Okay? And every path from R to T is an independent set, and therefore a color class. So I can find a solution by taking two paths, in this case, the blue path and the green path, 1, 0, 0, 1 and 0, 1, 1, 0, to find two color classes that cover this graph. This is the key to building our model. Is that okay? And here I'm doing something different than what was done before. So far, what we have done, we looked at decision diagrams as objects to find a single path. We were looking for the longest or shortest path. And now I'm using the same object, the same decision diagram, and have multiple paths. And they collectively are the solution. So a solution is no longer a single path. A solution is now a set of paths. And that's really, I liked it a lot because the decision diagram captures a lot of information. In fact, it captures sharply complete problems, if you wish, because you have all solutions right there. But I only look at it for getting one path so far. Now I finally have a chance to get multiple paths over the same structure. So that's something I very much like. How do I how do I find a solution like this? Well, I also have that ingredient. We knew what the network flow model over this diagram looks like. We did that in the integer programming case. I can do an arc flow formulation, and I have an arc variable right there. I want to minimize the number of paths in this case, because I want to minimize the number of color classes to find my solution. I still have my covering constraints. So for example, for, let's say layer 2, that's vertex 2, I have to pick exactly one of the one arcs, so that exactly one of the one arcs is in a color class, and the same for the other vertices. I have flow conservation and so forth. But this is the arc flow formulation we saw in the integer programming part. So it starts with the paths, and I impose on that additional constraints to making sure that I satisfy the constraints of the problem. And how do I solve this now? I cannot build an exponentially large decision diagram, obviously. So I'll start with a relaxation. The relaxation is again a very simple one for this application. I solve the network flow over this. I get a solution, the all ones path. It has a conflict. For example, I select 1 and 3, but there's an edge between 1 and 3. I have to fix the conflict. I refine the graph to eliminate that solution. And that's a column in the original formulation, so I'm eliminating the column from my original formulation. I update it, and I have a lower bound of 2, which is optimal, but I haven't found a solution yet because there's still in the flow decomposition into paths an infeasibility. But I keep on going, resolving this and refining and eliminating these infeasibilities until I reach a state in which I have no more infeasible paths that I have in my path decomposition. And now I've proved optimality. Okay. How well does this work? Well, let's have a look at the Dymax benchmark instances for graph coloring. On the vertical axis, the horizontal axis, I have the size of the exact diagram to prove optimality. If I give me an instance, I compile the exact diagram and I find the solution. Or on the vertical axis, I have the size of the relaxed diagram and do this iterative refinement. Do they exist, small diagrams, to prove optimality, or do I always have to go all the way to exactness? Well, this shows that very small diagrams actually can prove optimality. In this case, it's the DSJR500.1 instance with 500 nodes. The exact diagram needs at least 1 million nodes, but I stopped compilation after that. The relaxed decision diagram after this process of elimination and refining needs only 627 nodes to prove optimality. Note here, this is a graph on 500 nodes, 500 vertices, so the depth is 500. So you need at least 500 nodes to build the initial relaxation. And on top of that, I just need 27 refinements, in a sense, to prove optimality. So this can be extremely effective for some of these applications. I was very surprised to see this. So how does this work in general? We can do this either for linear programming or integer programming, and if you use integer programming, you get the actual integer solution, otherwise you get a lower bound, the linear programming bound. And we have applied this to other applications as well, together with my current PhD student, Anthony Karahelios, who's in the back. And he's on the job market, by the way, this year. And we found some other nice applications. We applied this to vehicle routing with time windows, graph multicoloring, and pickup and delivery problems with time windows. And we could actually solve, we are very competitive compared to the state of the art. These are not easy benchmarks at all. The graph multicoloring problem has been open for at least 10 or 12 years, I think. And so we close an open instance on 1,000 locations of the VRP with time windows. We close 5 open benchmark instances for the graph multicoloring problem and 6 open instances for the pickup and delivery problem with time windows. And this is all using the exact same framework. So this is a rather novel result, showing another application of this, integrating decision diagrams in integer programming and through column elimination. And with that, I'm done with my tutorial. We've seen that decision diagrams are a new tool coming from computer science for circuit verification and Boolean function representations, and they can also be applied to optimization. We can build standalone solvers. We can integrate them in constraint or integer programming in very systematic ways, and we can even build new and more involved technologies like column elimination to further integrate it and solve open instances. Thank you.